Without you, I would not start. So thanks all for coming. So I'm very pleased to have Tuukka Korhonen here, who's been like making all this progress towards our papers. Yeah, right. And he will talk about Treewidth, right? Dynamic Treewidth.
Yeah. Thanks for the introduction. Yes, I'll talk about dynamic Treewidth in logarithmic time. So just let's just start about talking about our dynamic algorithms. So what are our dynamic graph algorithms? So what is the setting? We want to design some data structure for maintaining a graph G and supporting some operations on the graph G. So so the most common setting is we want to have some initialization operation where we can create a graph, and often we just assume we just want to initialize with an empty edgeless graph, and then we want to be able to insert some edges to the graph and delete some edges to the graph, and we also want to be able to ask something about the graph. So and in this setting of dynamic graph algorithms, like the central algorithmic question is, can we support these operations faster than just recomputing the answer from scratch every time? Like, of course, you can answer the query by just using a normal algorithm every time the query comes, but maybe it would be interesting to if you could answer the query a bit faster by using the fact that the graph changed only very little after the previous time the query was made. So one traditional example of this is dynamic connectivity. So in this case, the query is we're given two vertices S and T. Well, this pointer doesn't really, but it's fine.
Oh yeah.
Now it's perfect. Yeah, we're given two vertices S and T, and we want to ask, are they in the same connected component of the graph? And for this, probably many of you know some solutions. So, okay, we can do the naive thing, which is computing from scratch every time. We can run some BFS or BFS in O of m time, where m is the number of edges. Then there is this union find algorithm that some of you may know works in this inverse Ackermann amortized time per operation. So it's really really fast, but it only processes these insertions, edge insertions, and not deletions. So this inverse Ackermann alpha here is some function that grows really slowly. It grows much slower than like logarithms or something. But then, if your graph is a forest, then you can then there's a data structure called Linka tree given by Slaughter and Darjan in the 80s. And you can do log n amortized time per operation. So each of these operations. Oh yeah, maybe I should say what is amortized time. So amortized time means that it's the average running time of the operation throughout like a sequence of throughout the algorithm.
So what do you mean by G is forest? You mean you want to maintain the graph is forest all the time?
So let's say we want to do dynamic connectivity under the assumption that the graph stays forest. That the user of the data structure never adds so many edges that there will become a cycle. Yeah. Yeah, so if the graph is a forest, we can do log n time, and this is actually it's a bit surprising because often there is no unconditional lower bounds in algorithms, but it actually has been proven by Eric Demain and Mihai Pătărescu that this logarithmic amortized time is actually optimal for dynamic connectivity, even when the graph is forest. Actually, even when the graph is just a set of paths, log n is optimal, and log n is optimal unconditionally without any hardness assumption. You can prove that it's optimal. And even when like amortization is allowed and randomization is allowed, log_n is optimal. And for general graphs, we know how to do dynamic connectivity in like log³ amortized time. This is still not known if you can do in logarithmic time. Okay, but this was some introduction to dynamic graph algorithms. Let me then go closer to the actual topic of this talk, which is dynamic Treewidth. So I'm not sure, I know probably most of the people here have seen the definition of Treewidth, but let me still go through the definition of Treewidth. So here we have an example graph, and here we have a tree decomposition of the graph. So Treewidth is a graph parameter that is defined via tree decompositions, and tree decomposition is a tree consisting of backs, and backs are just sets of vertices. And to be a tree decomposition, this tree of backs should satisfy some conditions. So every vertex of the graph should be in some back, and every edge of the graph should be in some back, meaning that both endpoints of the edge are in the back. So if you look at say edge between A and B, then there is a back containing both A and B. And third, for every vertex V of the graph, the backs that contain this vertex should form a connected subtree of this tree decomposition. So if you look at the vertex I, then the backs where I occurs, they form this connected region here. So this is the definition of tree decomposition, and now we can define the width of a tree decomposition in maximum back size -1. So this tree decomposition has width 2. And then we can define the tree width of a graph is the minimum width of a tree decomposition of the graph. And this graph, it turns out its tree width is 2. So we know, because here we have a tree decomposition of width 2, the tree width is at most 2, but we know that tree width is not less than 2, because tree width is less than 2 only if the graph is a forest. Yeah, and tree width was invented by many people independently of each other in the 70s and 80s under many different definitions, which turned out to be equivalent. Yeah, and why we care about tree width? Well, we care about tree width for many reasons in both algorithms and graph theory. But the main gist is maybe that the algorithms for trees, or any like graph theoretical results also for trees, often generalize to algorithms for graphs of small tree width. Say, for example, if we want to solve the maximum independent set problem, which is an MPR problem, we can do that in time 2 to the O of 2 to the k times n time on tree width k graphs. So n is the number of vertices. So you can do this by doing dynamic programming on the tree decomposition. And more generally, if you have a graph problem that you can define in so-called MSO logic, then there is this Courcelle's theorem that tells that you get a linear time algorithm for this problem, like linear time algorithm when the tree width is constant. Yeah. And there is a lot more of these algorithms for graphs of small tree width. And an important thing here is, at least for my research, is that in most of the results, most of the algorithmic results using tree width, you actually need the tree decomposition. So these algorithms do not simply work on tree width k graphs, but they work when you're given a graph together with a tree decomposition of width k. So it makes the problem of actually computing a tree decomposition of small width really important, because it's like whenever you want to use tree width, it's the first step that you do. You compute the tree decomposition. And there is actually a lot of research on computing tree decompositions. So a lot of algorithms for it. Here I mentioned just 3 out of very many. So you can, if you want to do it in like linear time when the width k is a constant. There is an algorithm by Botlander from the 90s to compute optimum width tree decomposition. But the dependency on the width k is a bit large, so it's 2 to the k cube. If you want to reduce that a bit, you can do this as the 2 to the of k. You can do a 2 approximation. And also, if you want a polynomial time algorithm for computing a tree decomposition, you can do, if you want, you can do with the square root of log k approximation ratio. And yeah, and in general, computing Treewidth is amply hard, and we also suspect that constant approximating Treewidth is not doable in polynomial time, but this is hard only under like this small set expansion hypothesis, which is not as established as p not equal and p. Yeah. So that's a quick introduction to Treewidth. Then let's go to dynamic Treewidth. So so given that Treewidth is very central in like graph theory and parameterized algorithms, many people have actually asked this question of dynamic Treewidth. Like, can we do Treewidth in the dynamic setting? Can we, if we have a dynamic graph, so a graph we want to support these insert edge and delete edge operations, and we want to also maintain a tree decomposition of optimal width, or maybe not optimal width, that's a bit too much to ask, but near optimal width. Can we do that in the dynamic setting? And yeah, so it was asked by Botlander already in the 90s, and then Dvorak, Kubec and Tuma, and also Alman, Mitch, and Wasilewska, Williams. And what we would also like to do, would like to maintain. We would also would like in this data structure for dynamic Treewidth to maintain some dynamic programming schemes on the tree decomposition. So like all of these applications of Treewidth, they need you to run, like typically how you apply Treewidth in algorithms is you run some dynamic programming algorithm on the tree decomposition. So to use actually some kind of dynamic Treewidth data structure for anything, we would need to ask it to also be able to maintain these dynamic programming schemes in the dynamic setting. So we have to do dynamic programming, and in particular, like we would like the main example of this is like the question of like dynamic Courcelle's theorem, whether we can maintain, if we have dynamic graph that is promised to be bounded Treewidth, can we maintain some MSO definable property of the graph quickly? Yeah, and there is by now quite some work on dynamic Treewidth. So like the first thing to mention is like Treewidth 1 graphs are exactly forests. So this kind of corresponds to dynamic forest, for which there is many algorithms with logarithmic of log and update time. So already this Limca tree of Slater and Tarjan, and then there's this topology trees of Fredriksson, and also these top trees of Alstrup, Holm, Lichtenberg, and Torup. And in particular, like it's not clear if you can like augment these older data structures to maintain like some dynamic programming for MSO properties, but actually these top trees of Alstrup and others, this is actually really maintaining a tree decomposition of which two of a dynamic forest, and it can directly be used for maintaining like dynamic programming schemes on this thing. Or actually, even more accurately, if you know branch width, then it's maintaining exactly a branch decomposition of which two. Yeah, and then there is also Botlander in the 90s did Treewidth 2 in logarithmic update time. So this maintains like decomposition of width 10 or something, but there is this I have to mention that this was a conference paper, and the full version never came, and it's missing some details, so it's not clear if this counts.
Which conference was this?
WG. Yeah. And then there's some prior results for Treewidth K. So actually, we can maintain some approximate tree decomposition in like n to the small of 1 amortized update time. But the approximation is also n to the small of 1. So this is a result of Courcelle from 21. So they have this. You might have heard of these expander decompositions of graphs, and they do this expander hierarchy, so hierarchy of expander decompositions, and this essentially corresponds to a tree decomposition, but with some caveats, like it works on edge cuts rather than vertex separators. So this kind of works only on boundary degree graphs. But it maintains kind of tree decomposition, but with n to the small of 1 update time. So yeah, maybe I should say something about this function n to the small of 1. So it's like a subpolynomial function. So it's like grows slower than n or square root of n or 100 root of n, but still faster than like log n or polylog n. Yeah. So this is a nice result. Sorry. But it has the caveat that the composition is like only n to the small of 1 approximately optimal. So it's not really suitable for like dynamic Courcelle's theorem, because it's not, even if you put like a constant Treewidth graph there, the decomposition maintained can have quite high width, and like Courcelle's theorem runs in like exponential time in the width. So it just doesn't do anything interesting in that case. Then me and my co-authors, we did also dynamic Treewidth data structure a couple of years ago with that means a Treewidth dynamic tree decomposition for Treewidth K graphs with some amortized update time. So now it's again this n to the small of 1 amortized update time, but now there's also some exponential factor on K in the front, but we get constant approximation. So so this is something where we get actually dynamic Courcelle's theorem with like sub-poly n update time. Yeah, and in this work now I have improved this running time quite a lot from to running like a logarithmic amortized time. And also the dependency on k is this 2 to the O of k compared to this 2 to the poly k. And it's a bit worse approximation, so it's only 9 approximation, but it's not a big difference between 6 and 9. And these two results, they support this dynamic Courcelle's theorem, so they support maintaining this dynamic programming scheme on the tree decomposition. Yeah. Are there any questions at this point? Yeah.
Just out of curiosity, the one of Goranci, Recke, Saranurak, and Khan, they have bounded degree, right? So does the exponent kind of depend on the degree bound?
It actually, I think, it's just the approximation. You get like a delta factor there.
Oh.
Yeah, I'm not sure, but I think it's just like that. It's so the structure kind of works naturally on edge cuts. So in worst case, like converting vertex separators to edge cuts makes you get like a delta factor.
So this can also work with carving width or tree cut width?
Yeah, probably. Like this works with more naturally, maybe with like carving width, I would say. Yeah. So everything clear at this point?
I'm curious about amortized time, right? So, how, like, given a sequence of insertion and add an edge,
Yeah.
leading edge, then you're estimating on the average time for
So
operation? Like
yeah, over like let's say like over the first T updates, the running time is like T times this.
And that's in the worst case.
Yeah, in the worst case, during the first T updates, the running time is T times to the O of K times log n.
I see.
Assuming you start with the graph without any edges. If you want to start with graph with some edges, then you also need to insert them first, and this can kind of make some strange things happen. Like once you have inserted all the edges, then the next operation can run very long, because you can kind of average from like all the previous operations.
I see. So when you measure this thing, then you assume the T is big enough.
I'm not assuming that T is big enough, but I'm just saying that I'm assuming that we start with the graph without any edges, and I was just saying that kind of to start with the graph with some edges, you need to first insert everything, in which case the first operation after inserting everything can take a long time if it kind of charges the running time for all the previous ones. Yeah.
So this can somehow be turned into a line approximation algorithm with running time n log n?
Yes. Yes, this can be, yeah, this trivially corresponds to the line approximation algorithm by just inserting all the edges one by one. Yeah. Yeah. Okay, good. Let me go forward, and let me make a more precise statement of this this theorem actually. So the statement is that we have a data structure that's initialized with the integer k and an edgeless n-vertex graph G, supports edge insertions and deletions in amortized time to the O of k log n under the promise that the tree width stays at most k and maintains a tree decomposition of width at most 9 times tree width times 9 times tree width plus 8. And it can also maintain any dynamic programming scheme on the decomposition within a similar running time, and this is formalized by tree decomposition automata. So tree decomposition automata is just like a kind of a description of dynamic programming, like describing how you can compute the state of a node based on the states of its children. Like you assume you have like binary decomposition, and then you give a description on how to combine states. Yeah, so we get dynamic Courcelle's theorem. And here, actually, an important thing is that the width of the maintained tree decomposition is at most depends on the current tree width and not this upper bound k. So it actually always maintains an approximation to the tree width. And this can be used to kind of remove this this promise condition, or at least like we can detect when this tree width actually grows too large. Like instead of having this promise, this can be turned into a data structure where like when I insert an edge, the data structure tells me that okay, inserting this edge for sure turns the tree width too high. So I will not accept these insertions. Please delete first some edges. Yeah, so it's the promise condition is not so restrictive, say. It can be removed kind of or relaxed in various ways. Yeah, but that's the theorem statement in more detail.
How much space do you have to do you keep? Like you have some data structure, right, to maintain?
Yeah, I mean the space is just like linear in n. I was thinking in the space there is maybe some to the k factor. I was thinking, is there even this? Maybe I don't need even any to the k factor. Maybe it's just like a linear in the size of the graph. Yeah. Yeah. So yeah, before going into details, let me mention also some applications, like why are we interested in dynamic Treewidth? Well, it's on its own. It's of course kind of natural question in the center of like parameterized algorithms and like dynamic algorithms, or like in the center of the intersection of these two fields of algorithms. But also like after this previous dynamic Treewidth algorithm that we did with people from Warsaw, we actually explored some applications of it. So like we used it to get this almost linear time algorithm for k-distant paths and h minor containment. So this as essential ingredient contains this previous dynamic Treewidth data structure.
You mean dynamic algorithm, or?
This is a static algorithm. This is a static almost linear time algorithm for k-distant paths and h minor containment. Yeah. So it's not about dynamic. You can use dynamic algorithms as an ingredient in static algorithms, and this is something that's done very often. And another thing like this was this dynamic rank width and rank width, like and rank width in almost linear time. So this previous dynamic data structure we generalized to dynamic rank width, which we then used also to get like almost linear time algorithm for computing rank width. And this is like linear in the size of the graph, not just the size of the matrix. And then like more recent work I've done with some people from in Copenhagen was we did like using dynamic Treewidth, we did like a dynamic kernelization with log and amortized update time for various problems. But for example, like planar dominating set, we can maintain a kernel, so a compressed graph with the same answer efficiently. Yeah, maybe I will not say anything more about these details. Okay. Okay, next I'll go to the actual algorithm. Any more questions at this point?
So this paper does it also contain rank width, dynamic rank width as well, or is
no,
it
this
separate
dynamic
paper?
Treewidth in logarithmic time, it doesn't contain dynamic rank width, and so it's like yeah, we have this a bit slower rank width dynamic data structure, and it's not yet written up whether we can also do that in logarithmic time, but it should be possible to do it in. It should generalize to rank width the techniques from here. Yeah, and it should speed up this rank width algorithm a bit to like this n to the 1 plus small of 1 should speed up to like n polylog n. Yeah. Okay. So let me then go to the details of the new dynamic Treewidth algorithm, which is actually much simpler than the previous dynamic Treewidth algorithm. So it's good. So okay. So first, let me tell about the like main invariants of this algorithm, like what kind of decomposition we maintain. So we actually don't do directly tree decomposition, but instead branch decomposition is the much nicer notion. And this is actually not like the traditional branch decomposition, which must have like a cubic tree, but this tree can have a high degree. So okay, what's the branch decomposition of a graph? It's so here we have a graph, and here we have a branch decomposition. So I say it's a rooted tree whose leaves correspond to the edges of the graph. Okay, so the leaves of this tree are labeled by the edges of this graph. And yeah, I know the normal definition says that this is like a binary tree, but now in this paper I allow the degree to be a bit larger than binary.
Do you allow arbitrary large degree?
There will be a bound of like 2 to the O of k on the degree. Yeah. And now I want to introduce some definitions. So I want to say that when we have some set of edges in the graph, so let's say this e.g. f, then the boundary of this set of edges is the vertices that are incident to edges from both f and its complement. So now the boundary of this set of 3 edges is these 3 red vertices. So yeah, so the middle one is not on the boundary because all of adjacent ones are in red. And then I say that the set of edges f is well linked if we cannot partition the set of edges into 2 parts, C1, C2, so that the boundary of C1 is smaller than the boundary of the set f, and the boundary of C2 is smaller than the boundary of f. So this is kind of it's maybe not so clear definition, but there's also like more intuitive version of this definition, what it really means. So it really means if you think about your set of edges f, and then you think about the vertices on the boundary. So this is like this is the boundary. Okay, how I write this boundary of f. Then what this definition, an equivalent definition to this, is saying that whenever you choose 2 subsets of the boundary, then you can route them into each other using edges only in f with like vertex disjoint paths. So you can, whenever you choose like set A and set B that have the same size on the boundary, you can route them by vertex disjoint paths into each other. And these sets can also like overlap. Like you can have like this, in which case you route these vertices into overlap by disjoint paths of like trivial one vertex paths. You route them like into itself. So this is what it means to be well linked. And this equivalence is by like by Menger's theorem. Yeah. Okay. And now the crucial invariant in this data structure, the crucial graph theoretical invariant, is we want to maintain that if we have a subtree of this branch decomposition that corresponds to some set of edges, then this set of edges should be well linked. And I call this invariant downwards well linkness. So I want to say that kind of, if I think about the boundary here, then it's like well linked through like a downwards direction. And indeed this you can check that this set of edges e.g. f is actually well linked. You cannot partition. If you remove an edge, you will still get a boundary of size 3. Is this definitions good? Yeah. And so now what we get, why we care about well linkness is that there is a nice connection to Treewidth that actually, maybe I should write here a lemma that if if f is well linked, then the boundary size of f is at most I think 3 times Treewidth of G plus 2. So if I'm kind of in front of this, but I hope you see it. Yeah. So if you have a bounded Treewidth graph, if you have Treewidth K graph, then all of these boundaries will have size O of K.
Not the branch width, tree width?
I mean they are within constant factor of each other, right?
Yeah.
Oh, maybe it's 4. Maybe it's 4.
I think it's 3.
You think 3 is enough?
I think 3 should be enough.
Yeah, let's go with 4 to be sure.
You want to be safe.
Yeah, it doesn't matter much. So
Yeah, I was wondering, like, as you're expressing everything in terms of branch decomposition, so yeah, I was surprised to see tree width instead of branch width.
yeah, but it's it doesn't matter if you just want to say that it's O of K. It's O of K for both is the same. Yeah. Then we also want to maintain that the degree is at most 2 to the K. And now what happens is that now you can think when you have a bounded degree in this kind of decomposition, you can think how it corresponds to a tree decomposition. So what we can do, we can like look at the node, and then we can look like all of the edges adjacent to that node. There is some boundary corresponding, like the boundary of the subtree below it, and it turns out that if you take like the union of these boundaries, so you make it like a back, and now you get the tree decomposition. So now you can say like the back of this node. This is just the union of the boundaries of all adjacent edges. Let's say boundary of let's say xt, where like let's say x ranges over the neighbors of t, and the boundary of xt means the boundary of the subtree corresponding to that edge. And you can it's not too hard to prove that this is actually a tree decomposition. Like this is the basic way to construct a tree decomposition out of branch decomposition. And the width of this tree decomposition will be like the degree times the boundary size. So we get a tree decomposition of width 2 to the O of K. And I guess, yeah, in this talk I will not tell how to optimize this to O of K. Like basically, yeah, this can be optimized to O of K by later just replacing each node by like internal tree decomposition. But this is already this 2 to the O of K already is sufficient for many applications, that it captures like the main contribution. So let's just focus on that. Yeah, and also we want to maintain that the depth of this decomposition is at most this 2 to the O of K times log n, because it's kind of a natural thing in dynamic trees to have a log n depth tree, because the running time of operations will depend on the length of root leaf path. Yeah, so this is the basic invariance, and now let's look at basic ways how we will edit this decomposition. So we now want to maintain this kind of a structure under like insertions and deletions of edges, and we will actually do this by using 2 different like basic local rotations. So one of them is contraction. So if we have our branch decomposition here, and we have an edge of it here, then we can just contract this edge to get another branch decomposition. And this can be done locally very fast, and when the degrees are bounded. And we can see that this maintains downward spellingness, but increases degree. Then we have another operation, which is used for decreasing the degree, which is a splitting operation. So what we can do is, when we are given a node with high enough degree, so the degree it needs to have is like some exponential in k, what we can do, we can locally split it to multiple nodes. So here, like this node here, it has like 4 children, and we split its children into 2 groups here. We split it into 4 children into 3 children. Yes, we split like into EF, and then this combination of G and HI here. And this is a non-trivial lemma that this splitting can always be done so that downwards well-linkness is maintained. And I think I want to say something about how to prove this lemma, this splitting lemma. Oh, and we need one more thing. We need that we can also, in the splitting, what's important is that we can choose some set of like constant number of children that will not be pushed deeper. So you can think of this splitting as pushing some children deeper, like merging some children together and pushing them deeper, and keeping some children into place. So we can choose some children that will not be pushed more deep. And what's the idea of this this splitting operation? So first thing is that when we have a node, we can think of a hypergraph where the hyperedges are these boundaries of its adjacent edges. So we can think of torso hypergraph. So hypergraph is for me is just a graph where instead of edges we can have edges that are actually just sets of vertices. And we can define well-linkedness in hypergraphs in the same way. So we can define that a set of hyperedges is well-linked if you cannot split it into 2 so that both of them have a smaller boundary. And now what we can say that actually in this torso hypergraph, if we have a set of hyperedges corresponding to some set of children, and this set of hyperedges is well linked in this torso hypergraph, then actually when we expand these hyperedges to include like all of the actual edges that are in the leaves below them, so we expand this to include all of this subtree and this to include all of this subtree, then we have that this is expanded thing is well linked if and only if this condensed thing is well linked. So this is if and only if. One way is easy, so it's so we want that set in torso is well linked if and only if corresponding set in G is well linked. And yeah, the if direction is the easy one. No, the only if. Okay, like if we have that this this thing in the torso is not well linked, then clearly you can have the same partition of the edges and they have like the same boundary, and then it's not well linked. But then it's hard to say that that actually if something is well linked in the torso, then it's well linked in the whole graph. And this requires some proof. And the idea of this proof is basically this: we use the fact that this is downwards well linked. So we use that kind of if we have some boundary here, and you can route some stuff by using these hyper edges, then actually you can use this well-linkedness to say that the same the routing in this hyperedge can be always replaced by routing with actual edges of the graph. Like the connectivity of the graph when you have a well-linked set can be just condensed to the connectivity of the one hyperedge corresponding to the boundary of that well-linked set. That's kind of the main graph theoretical thing here, and that's like the main graph theoretical reason why well-linked sets are so nice in this context, that they can correspond like the connectivity information to such small representation. Yeah, so now we just need to show that that if this torso hypergraph, if it has too many hyperedges, okay, so we want to show that lemma, then we can choose some subset of them that is well linked, and then we can this subset can be chopped away. So you think if you choose like at least 2 children, so that there's also some other children left, and then you can and this set is well linked, then you can split this set off. So what you do, you use the fact that your graph has bounded Treewidth, and you have like this property that for well-linked sets the boundary is small. Okay, what do you do? So yeah, you start by yeah, let's say you have like at least 1 or at most 3 children that you want to ignore, that you don't want to drop deeper. So you take like everything else. You take all the other children, and now you get some set of children with some boundary size like let's say 2k. So if you ignore like 2 hyperedges, so you always leave out the parent hyperedge, and you leave out one child. So now you get like a boundary. If you look at the rest, you get the boundary of size at most 2k. And now you want to say, if I have a set of hyperedges that is large enough and has small boundary, then inside I can always find a set of hyperedges that is well linked. And how this works is that okay, if I have, okay, let's draw it again to be more clear. So if I have this set of hyperedges, it has some boundary, but it's not well linked, then I can partition it into 2 sets that have a smaller boundary. This was the definition of well linked. And then if I had enough hyperedges, so let's say I had initially like at least 2 to the b hyperedges, where b is the boundary size. Now one of these sets will have at least half of the hyperedges. So I have at least 2 to the b minus 1 hyperedges in a set whose boundary size is at most b minus 1. So now I can repeat this argument to in the end. So now I can again here I have okay maybe a lot of hyperedges, and if they're not well linked, I just separate, and I can zoom in and still find, if I started with enough hyperedges, I can zoom in and find a set of hyperedges that that must be well linked. So that's how I get this splitting operation. So yeah, and the point here is like all of these computations, they run locally in this like torso hypergraph corresponding to this node, which has like at most size like 2 to the O of k. So you can run this. So it doesn't matter much like how you implement this. It will run quite fast, and you will only need to look to this particular node to implement these things. So you can think of that this splitting thing. Yeah, you can make it run in like 2 to the O of k time. So yeah, so these are the two operations we have for editing this branch decomposition. And yeah, now our goal is to support edge insertions, edge deletions, and maintain this invariance that we want to maintain. So okay, let's go to inserting and deleting edges. And here we have some technicalities. So now I have to reveal that actually in the branch decomposition we don't have just the original edges, but we also have like self loops. Like we have edges corresponding to just one vertex, like what I call like self loops, just to make things a bit nicer. So these self loops basically they don't do anything else except they affect the boundaries maybe at some places. Yeah. Now, what to do to insert an edge UV? So what we want to do, we want to use these contraction and splitting operations to ensure that the self loops corresponding to U and V are children of the root. So it's like what you do basically is how to make some leaf. So these self loops, they correspond to some leaves of the decomposition. And if you want to make some leaves closer to the root, so you can do just, let's say you want to make the leaf corresponding to E closer to the root. So you contract this edge, it gets closer to the root. And then you want to decrease the degree. So you use the splitting thing to split something off, but you tell the splitting that you don't want to split this E any deeper. Because I mean you can do this with this this thing. So now you maintain the degree, and this leaf gets closer to the root, and you repeat this until you make it a child of the root, and you do this for both of these self loops. And now the point is, okay, why we want to do this is that after this UMV are children of the root, then inserting the edge UV as another child of the root is really simple. Like the point is that now we can just insert this UV as another child of the root, and it doesn't affect the boundaries anywhere else in the decomposition. Like the problem with like kind of inserting UV arbitrarily is that it can affect the boundaries globally in the decomposition. But if you have this starting point where U and V are in the same place already, then it doesn't affect the boundaries anywhere. So you can update the decomposition really easily. So basically the only thing that's difficult here in the insertion is this doing this sequence of local rotations to make these things children of the root. And the same thing works for deleting an edge. But just with the three leaves. So we have these leaves corresponding to UV and UMV, and all three we rotate to be children of the root, and then deletion is again easy, and updating decomposition is easy. Yeah. Okay. But there is one more thing. There is like we have this. These nice rotations to rotate stuff close to the root, and this is what we do repeatedly. And we have this splitting to control the degree, so this is fine. But these still doing these operations, they increase the depth of the decomposition. Like we still have to control the depth of the decomposition we have. So we wanted to have logarithmic depth, in particular because this rotating the root, of course, takes like at least log n time for sure. And I mean, it can be done with like log n or like to the of k log n operation, this relation to the root. So now we have something else for controlling the depth. Okay, so here's some definition. Size t for node t is the number of leaves below t. And what we want to maintain an invariant that if we have a node B that's descendant of a node A. So so node A is maybe somewhere here, and then when you go to like child and main child down, you meet the node B. If it's a descendant with a large enough distance, the distance at least some f of k, which is in 2 to the of k, then we must have that when we go from A enough steps down, then the subtree size halves. And this condition implies that the depth is controlled. Yeah, because it just means you cannot have too long root leaf paths. And then we have a potential function. So this is where the amortized analysis comes from. Is we do a potential function of where the potential of a node is the degree of the node minus 2. So it's the number of children minus 1 times logarithm of this number of leaves below. And the potential of the whole tree is the sum of the potential of the nodes. And this is actually really important that this is exactly degree of t minus 2. Like the minus 2, it wouldn't work for any other number than minus 2. So this is, if you've seen splay trees, this is basically a generalization of this potential function of splay trees to trees of higher, more than 2 children. And then we have a lemma that if we have this kind of pair of nodes where we have some node B that's descendant of A, but it has too large size and it's too close, then we can decrease the value of this potential in time that's proportional to the decrease. So what we can maybe I want to say it better. We can turn t into t prime, so that the potential of t prime is strictly less than the potential of t, and the running time of this is like some factor. Okay, maybe let's do to the of k factor times potential of t minus the potential of t prime. So it decreases the potential and runs in time that's proportional to how much we decrease. And what's the main idea here is like you imagine this this long path from A to B, and you have here like this, and you imagine you have here this subtree that contains still most of the descendants of A are in this subtree. And now you want to turn it into a much nicer form where you have A and B is just directly a child of A, and all the other stuff is in this another subtree. So you want to rearrange this essentially this kind of form. Yeah, I'm not sure. I'm running out of time, so I probably shouldn't go into detail of how you count the potential here. But the point is like essentially the sum of this. The sum of this thing of degree t minus 2 is the same like here and in this rearranged subtree, but in this rearranged subtree you have a lot of nodes where this log size is like better by 1, basically. Like in all of these, you imagine that they went into here, and the log size went better by 1. And there's some 2 to the O of k things involved and things like this. But that's the idea. But and this is all like inspired from the splay trees. Like this is essentially same kind of stuff that happens in the traditional analysis of splay trees. Yeah, and then we need another lemma that says that like basically when you do edge insertions and deletion, then the potential grows a bit, but not by too much. It grows by at most like log n times 2 to the of k. So basically it's like the potential by doing like one local rotation can increase potential by at most 2 to the O of k, and then you do like log n local rotations to rotate things up to the root. So this thing happens, and now these two things combined give the running time, give the amortized running time, and it's amortized because like in one iteration you may have to do a lot of work to decrease the potential, but then you increase the potential very slowly after that. Yeah. Okay. And I guess, yeah, that's all I want to say about the algorithm. So in conclusion, we have some dynamic algorithm for maintaining a tree decomposition of small width. And we can also maintain dynamic programming schemes on the tree decomposition. And there are some open problems still, like this kind of solves dynamic tree problem quite well, because you cannot do really better than log n, because even for dynamic forests you need log n. And also like this 2 to the O of k is kind of optimal because, well, even for approximating Treewidth in the static setting, there's nothing known in like if you want to do constant approximation, it's not known if you can do better than 2 to the O of k factor there. Yeah, but there's one question: can we go from amortized running time to the worst case running time? And can we rule out a running time of form like f of k plus O of log n? So here we have f of k times log n, but f of k plus log n. And I think really that we shouldn't be able to do this kind of update time, but I'm not sure if it can be proven that we can do it. And then there is a question also about the approximation ratio. So here is 9 approximation, so you can imagine improving it a bit, but there is a lower bound. So this is not published, but I think I have proven this, that if you want to explicitly maintain a tree decomposition in the dynamic setting, where you actually want to represent the backs and so, then you cannot do better approximation ratio than 3 if you want to do logarithmic time per operation. And that's all. Thanks.
Thank you. Any questions? Yes,
So you maintain a branch decomposition, right? So all of this also works for branch width?
Yes. Yeah. It's
Yeah.
yeah. You can. It works for Treewidth and branch width, and you get slightly different approximation ratios, I guess. But yeah.
So you kind of said something about my next question in the very beginning, but I want to phrase it like slightly different.
Yeah.
Suppose I give you some graph and a bounded with branch decomposition for the graph. And I give you some other graph and like a kind of an exchange pattern. So you can go from G to G prime by deleting and adding some edges.
Mm-hmm.
And you have a good decomposition for G. Can I somehow compute the setup for this and then compute these update steps to go to G prime?
Wait, did you also get the decomposition of G prime?
I don't have one for G prime. I only know the one for G.
Yeah, I mean, I guess you can just, so you want to have a given decomposition, and this given decomposition you want to edit. So I guess, I guess it depends on
or at least use it to compute a setup from where I can start updating. So I allow you to change this one.
I mean, you can just kind of start with the. Oh no, you cannot start with the decomposition because you want the downward swellingness and all that. Yeah, it's. I'm not sure if it's that useful to have the decomposition ready, because it's kind of not suitable for anything if it's just arbitrary decomposition. Like you need to have like this logarithmic depth and this downwards well linkedness and all this extra stuff to for it to be useful.
There's some background for this. So
Yeah.
apparently Paul Seymour and Bill Cook computed a bunch of telephone networks and their branch width in the mid-90s.
Yeah.
And I imagine these branch decompositions from back then, they're not up to date anymore today, but maybe there's a way to kind of update.
Yeah. Yeah. I mean, you can. I don't think that having the original decompositions helps too much. Yeah.
If it's from the 90s, probably the part which is already known is like an epsilon proportion of the
I
curve
guess so,
one.
yes.
So
Yeah.
Oh, where does the 9 come from?
Yeah. The 9 comes from 2 places. So we had here basically this thing, this bound on. You want to say that the boundary of Welling set has some size bounded by Treewidth. So you get 1 factor there. I think it's 3 actually here.
Yeah.
and then you get another factor 3 when you go to like another direction. So you want to say that, okay, so how we go, so we have these torso hypergraphs, and then in the end we want to put on each node, we want to, instead of have 1 back, we want to put there like a 3 decomposition of this torso hypergraph. And here we want to say that the Treewidth of this torso hypergraph, it depends on some things. So it depends, but you can bound it by like the well-linked, the largest boundary of a well-linked set in this hypergraph. So you must bound it by like this. So you kind of go from Treewidth to well-linked set boundary and back from well-linked set boundary to Treewidth. And in both steps you get like a factor of 3. Yeah.
I wonder, I have maybe one, so here's one live question. And so path width might be much more difficult because we don't have a well-linked concept, right?
Yeah. I think path width is should be really difficult because it doesn't have very nice graph theoretical properties. Yeah.
And
But it's like for path width is a question of like, I mean, the value of path width you can maintain because you have a dynamic programming algorithm for computing the value of path width that runs on graphs of bounded Treewidth. So you can just do the dynamic Treewidth algorithm and then maintain dynamic programming. So the value you know, but the decomposition, maintain decomposition could be hard.
I see.
Yeah.
And if I restrict to planar graph, and then there's polytime algorithm to compute branch width.
Yeah.
I wonder whether we could have dynamic optimum branch width algorithm or some constant factor branch width algorithm for planar graphs.
Yeah, like in the dynamic setting. Yeah, I don't know if I have no idea how planarity would help in these things. It sounds really hard. I mean, I guess this I mentioned this. Okay, it's in the very beginning. I mentioned this data structure of some people for maintaining this. Oh yeah, here, like this one. I mean, this you can apply, but and you get like under the small of 1 approximation and only 1 degree. I was wondering maybe you can remove the boundary degree assumption by doing some the rat catching thing and going to carving width and yeah. But that's also, it's not clear if you can do it dynamically because you need some embedding and yeah. So I don't know much about the planar case now, and I have no idea how it could help. Also.
All right. Any other questions? Okay, if not, let's think.